So welcome everyone to the first SSA ACT branch meeting of the year. My name is Francis. I'm the current interim president. So just a bit of housekeeping first for those who are, I guess, online. Please ensure you mute your audio to minimize feedback. And we'll be leaving questions until the end of Bronwyn's talk. If you're at the end and you do have a question online, if you're online, you have a question to ask, and you can ask it in the chat. Or you can unmute yourself and we'll try to answer it then. Obviously, if you're in person, we can just deal with that. We will try to repeat the question so that everybody, both online and in person, can hear. Also, note the meeting is being recorded and will be made available publicly afterwards. Now, I do want to start off by also giving a bit of a general spiel, although most of you should be aware. The SSA is the national body that represents statisticians from all across Australia. And so if you want to know more about the various events, workshops, talks, like this fantastic one, etc., going on both locally as well as nationally, please do not visit www.statsoc.org.au, just visit statsoc.org.au. We've learned that today. The 3 W's no longer, it doesn't work anymore, apparently. So anyway, that's something we found out. So yeah, anyway, so just Google Stat Society of Australia and go there. Okay. Sorry, that was a tangent. Okay, so today it's my great pleasure to introduce Dr. Bronwyn Long, who is a senior lecturer in statistics at the ANU Research School of Finance, Actuarial Studies and Statistics. Her research interests are in missing data confidentiality, causal inference, and Bayesian modeling. Bronwyn enjoys working on applied problems with particular applications in medicine and healthcare. And today she's going to be talking about treatment effect estimation with entropy balancing and observational studies, and joint work with Gen, who's just arrived, as well as Raymond as well, both of them are. So please join me in welcoming Bronwyn.
Well, good evening, everyone, and thank you for coming. And I'd like to start by just thanking Francis and Warren from the SSA Canberra branch for inviting me to speak today and organising the venue and the dinner afterwards. And I also want to acknowledge my co-authors in this piece of work. This is joint work with Professor Raymond Lill and Dr. Gen Nowak, who is also here, also from the College of Business and Economics here at the ANU. So my talk today is on treatment effect estimation with entropy balancing and observational studies. This piece of work stemmed from Raymond's work as a medical practitioner and researcher being involved in observational studies in the healthcare medical related area. And entropy balancing is a relatively new technique that's been around that people are using to estimate the treatment effect in an observational study. We know in an observational study, we don't have the benefit of a randomized assignment mechanism, so we have to deal with the presence of confounders, and which can, of course, bias our results. So my talk today, the first part, will review the key literature on entropy balancing, so you know what it is. And then the second part, I'll go over some of our simulation studies that we've run, that we ran to answer some of the outstanding questions that we identified in the entropy balancing literature. I'll let you know now, this is not a very technical talk. I think that aligns with how I think. I'm not a very technical person, but then hopefully in that sense, this talk will be accessible to a good portion of you. Okay, so before we get into entropy balancing and what it is, let's just take a step back and talk about causal inference in general. So what do we mean by cause and effect relationship between two variables? So suppose I have a treatment and I have an outcome Y, and what I want to try and identify if the treatment has a direct influence on the change in your outcome Y, and that change in Y is not influenced by any other variables, whether observed or not observed. So it's a very specific set of conditions that we need to satisfy. Of course, we all know that randomized control trials are the gold standard to establish causality between two variables. And why is that? Okay, so in a randomized control trial, we randomly assign our units to treatment or control, and that ensures on average that the treatment and control groups have similar distributions of observed and also related unobserved covariates. So that means in expectation, that makes the treatment independent of both the unobserved and unobserved outcomes. So we can just take the difference in, say, your sample means between the treatment and control group to estimate the treatment effect. Okay, but we also know as well that in a lot of cases, it's unethical and not feasible to conduct an RCT. So, for example, it will be unethical to assign people randomly to, say, a smoking group. Okay? Also, it takes time and money to recruit a large enough number of participants that meet the study criteria and monitor them over the study period to make sure they adhere to the treatment protocol. So we have observational studies as an alternative. In an observational study, we study a group of units in the population, but we don't have any control over the treatment. So we don't assign any treatment. We don't assign any units to a particular treatment. And so we lose that control over the randomized assignment mechanism, okay? But then, of course, we have to deal with the presence of confounders. Okay? So causal inference in an observational study is not so straightforward. So here, I've just briefly summarized as background information the key differences between an RCT and observational study, so we know the setting that we're dealing with, okay? So just to reiterate, treatment assignment in an RCT, it's random, it's known, and it's under the control of the research. Okay, we lose all of that in an observational study. The treatment assignment is not random, and furthermore, the true assignment mechanism is unknown. So in matching-based methods, modeling-based methods for matching, we actually try and make assumptions on what that true assignment mechanism is. Okay? So in an RCT, because of the randomized assignment mechanism, we don't have to deal with compounding variables in expectation, which makes causal inference a lot more straightforward. Okay? Obviously, with observational studies, there are potential compounding variables when your covariates are related to both the treatment assignment and the outcome, and therefore we need to make adjustments in terms of how we estimate the treatment effect. Okay, so our goal in treatment effect estimation and observational studies is to try and replicate some of the characteristics of an RCT. So here I've just listed some of the methods that you may be familiar with. Okay, so first up we have a regression-based estimator adjusted for background variables. So that's a very straightforward approach. You fit an ordinary least squares model with your response. The response is your outcome variable. You have an indicator for your treatment, assuming a binary treatment, and then you adjust for a bunch of background variables on which you have data available. So the coefficient estimate for your treatment indicator will be your treatment effect estimate. Okay, so that's a very simple approach, but doesn't do so well when there's a lack of overlap between your treatment and control distributions. Obviously, it can't adjust for unobserved variables, and also won't give you very stable estimates if you have a very small number of treatment units compared to your control. Matching methods, okay, and under this matching methods, we have propensity score methods, which I'm sure many of you will be quite familiar with. So here we're using matching not just to refer to exact, say, one-to-one matching or matching by some distance metrics such as Mahalanobis distance, but also broadly referring to any technique where we're trying to equate or balance the distributions between our treatment and control. So we can also be weighting, for example, by the propensity score, or classifying by the propensity score being defined as the probability of receiving the treatment conditional on a set of covariates. Okay, but of course, you need to make assumptions when you're making defining your propensity score model. Okay, you're making an assumption on what that true assignment mechanism is. Okay, and you also need to make assumptions on how quality is a match. How do we find a good quality match? How large should our control pool of matches be? Okay. Instrumental variable analysis, very common in the econometrics literature. So instrumental variable analysis, you have a variable, say Z. It's not correlated with any unobserved variables. It's associated with the treatment effect, and it's only correlated with the response through its association with the treatment. Okay, so the idea is if you do find a correlation between the instrumental variable and your outcome, that may be attributable to a causal relationship between the treatment and the outcome. Okay, but of course, finding an appropriate instrumental variable for which you have data available, that may not always be possible. Entropy balancing, which is the topic of my talk today. We could take a Bayesian approach, so assign price to our parameters and generate posterior predictive distribution of the treatment effect estimate accounting for uncertainty for the potential outcomes. Okay, so I've just listed probably the more common methods that you may have come across. There are probably other methods that exist for treatment effect estimation in observational studies. But for this talk, we'll be focusing on entropy balancing. Okay, so entropy balancing was proposed by Haymuller in 2012. So relatively speaking, it's a fairly newish technique, but it's based on a very established idea in the survey literature on reweighting schemes to match survey population totals with totals known from the auxiliary data. Okay, but its application in the causal inference space is relatively new. So it's a pre-processing technique, and it's designed to achieve covariate balance in observational studies with a binary treatment. Okay, so the output of your EB algorithm is a set of weights, and those weights are determined such that the control group sample moments are matched to the covariate moments in the treatment group. Okay, so the moments that you match could be to the first order, the second order, third order. So the order of the moments that you match is a decision that needs to be made, as well as what covariates you're balancing on. Okay, obviously, the more covariates you balance on and the higher order that you're matching on, that increases the number of balancing constraints that you have to satisfy, and you can potentially run into convergence issues with the algorithm, and we'll talk a bit more about that. Okay, but the idea is pretty straightforward. Okay, we're specifically solving for those weights for the control group such that we match the sample moments, essentially equating the covariate distributions up to the highest order moment that you choose between the treatment and the control. Okay, all your treatment group units are assigned a weight of 1. Okay, and it's only the control group units that we reweight. Okay, so before getting into what EB exactly is, I'll just introduce some notation. So consider I have a random sample of n units, NC of them are control units, NT are treatment units, and I'll let T be a binary treatment indicator. So just consider the simplest case of a binary treatment, okay? X as a vector of K observed characteristics for unit I, and YI is what we're using to denote the observed outcome. Okay? Under the potential outcomes framework for causal inference, which was proposed by Rubin in 1974, we express the observed outcome as a linear combination of the two potential outcomes. So YI1 is the potential outcome that would be observed if the unit were assigned to the treated group, and then YI0 is the potential outcome that would be observed if that unit were assigned to the control group. Now, of course, each unit is only assigned to either one or the other, okay? So we only observe one of the potential outcomes. Okay. So in terms of estimation of the treatment effect, here we use the notation tau I to denote the treatment effect estimate for unit I, okay? So that's the difference in potential outcomes for that unit, YI1 minus YI0. Okay? In terms of estimating the population average treatment effect, we can define that over the entire population, so that's PATE. And so that's the effect of moving the entire population from the control to the treated group. Or we can also define the population average treated effect of the treated, PATT, okay? And so that's the treatment effect, but defined only on those units who ultimately receive the treatment, okay? So the key thing to note here is this second quantity here, E of Y dot given T is equal to 1. That is obviously the potential outcomes under the control for those in the treated, okay? And that is obviously the counterfactual, meaning it's unobserved, okay? But that's okay in an RCT, okay? Because in a randomized control trial, the randomized assignment mechanism is known, and the groups are only randomly different from one another on all covariates observed and unobserved, okay? So we can actually, to estimate the counterfactual, we can actually use the quantity that we do observe, okay? And so that's why in a randomized control trial, you can just take the difference in sample means to estimate the causal effect, okay? But of course, we can't do that in an observational study because there are systematic differences between the treatment and control group with respect to the covariate distributions. So we need additional assumptions to be able to estimate the treatment effect in observational studies. And what are those assumptions? So these assumptions were set out by Rosenbaum and Rubin in their 1983 paper when they first introduced the propensity score method, and they apply here as well. So the first assumption is the assumption of strong ignorability. Okay, so what that says is that the treatment assignment or your exposure to the treatment is independent of your potential outcomes given the set of covariates, given a set of baseline covariates. So in other words, that means there's no unmeasured confounding. The second assumption is called the overlap assumption. So in words, it means there's a positive probability of receiving each treatment for all values of X. So in other words, the distributions of covariates in X, covariates X in the treated and control groups overlap. Okay? So there's some positive probability of being either in the treatment group or control group. Okay? So now we're going to talk about how EB satisfies these two assumptions of strong ignorability and overlap. Okay, so to do that, let's specifically talk about what EV is. Okay, so the output of your EV balancing scheme is a set of weights, we'll call them WI, okay, and they're assigned to each control unit. So how do we find those weights? Well, they're found by this solution to this optimization problem. So here I want to minimize this loss function, okay? And I'll talk about what that loss function is subject to these constraints, okay? So we have a set of balancing constraints, okay? These are the balancing constraints where we're equating the weighted moments of your control group to the sample moments of your treated group, okay, across all of your K variables up to the arc order. Okay, so arc will be first order, second order, third order. Okay, and then also the normalizing constraints that the sum of the weights over the control group must equal to 1. Okay. Okay, so what is that loss function? So the loss function is a distance metric between the estimated weights and a set of base weights. So Haymiller in his paper used the Kullback-Leibler divergence as the distance metric and assumed uniform weights as a set of base weights. So the base assumption was that all of the control units are equally weighted. Okay. MPAT RK, that's the R sample order moment of a given variable xk, and we want to equate the sample moment of a given variable in the treatment group to the weighted sample moment in the control group. Okay. So to solve that numerical optimization problem here, to find the set of weights that minimizes this loss function subject to these constraints, okay, requires a numerical optimization algorithm. The algorithm used in Haymiller's paper was the Levenberg-Marquardt algorithm, which is based on the Gauss-Newton algorithm. So the actual algorithm, provided you can get a solution, okay, is not too difficult to understand. Okay, we've got a defined loss function that we want to minimize subject to a set of constraints, and those constraints are specified specifically to equate your covariate distributions up to a certain order. Okay, so why does EV work? Okay, how does it satisfy those assumptions of strong ignorability and overlap? Well, the EV weights, they orthogonalize the treatment indicator with respect to the covariates included in the EV weighting up to the arc order, okay? Because we're specifically solving for those EV weights such that the covariate moments between the treatment and the control group are equal. Okay? And then secondly, if you can find non-zero weights, if your when you run your EV algorithm, if you obtain a solution, then your algorithm has converged, okay? And it can only be converged, it can only converge if there's sufficient overlap, so some level of common support between the treatment and control group. So the overlap assumption is therefore satisfied. Okay, so on the next few slides, I'm just going to go over some of the key recent literature in the EV space so you can have an idea of what's been done. And this was important as part of our research process so we could identify what are the key outstanding questions that are remaining to be addressed. So there has been some theoretical work, not a lot, okay, but some theoretical work. So Zhao and Percival in 2017 demonstrated that entropy balancing is doubly robust. So they used theoretical work to show that entropy balancing is equivalent to fitting logistic regression for the propensity score model and a linear regression for the outcome model. And the predictors of those regression models are the covariate moments that are being balanced. Okay, and what they showed that was the EV estimate of the treatment effect was a consistent estimate, provided that at least one of those models was correctly specified. This second paper here by Karlberg and Warburg in 2023, they derived the asymptotic variance of the EV estimator for the population average treatment effect of the treated. And then this 2022 paper extended Haymiller's work to consider the case of a continuous treatment. Okay, so there's been a bit of theoretical work done, but at the same time, it's still a bit of a black box. There's this algorithm, you get your weights, and it gives you a treatment effect estimate, and its properties have more been demonstrated through simulation studies rather than actual deriving any specific results. Okay, so in terms of those simulation studies, there have actually been quite a few. And the interesting thing is most of those studies have compared EV to propensity score matching. And I think that's because propensity score matching is probably the most commonly used and wide accepted method for treatment effect estimation in observational studies. So it's been like the default benchmark to compare against. So here I've just listed a handful of those studies. There have been simulation-based studies as well as studies based on real data. The common thing, the common finding amongst all of these studies was that none of these studies found a single best strategy across all the simulation studies. Okay? And they didn't identify specific conditions under which propensity score matching outperformed EV or vice versa. So to quote from one particular paper, and I'll just read it out here, one of these papers concluded it is difficult to be able to project which propensity score balancing method will do best in any given study, and thus we believe it is better for it to become standard practice before looking at any outcome models to use multiple methods and carefully compare balance and select the one that is optimal. So it's basically like do everything and then select the best one. So it's pretty inconclusive, very open-ended, not very constructive. Okay, so
that's the biggest treatment effect.
That's right. Yes, that's right. That's the one that works at So that's probably what they did. Yeah. So of course, this list of this didn't feel like we gained much knowledge from those studies either. Okay. And there have actually been a few studies that have actually focused more on the shortcomings of entropy balancing. So here I've just listed a couple of them. So the first paper actually comes from an accounting paper. They were comparing big audit firms with smaller size firms and comparing the audit income that they were able to generate. The second study focused also on the rollout of a patient-centered primary healthcare model and whether the rollout of that program had any effect on changes in Medicaid costs. What both studies encountered with their real data was that the EV algorithm on a small set of observations produced excessively large weights. Okay, so that small set of observations had disproportionately large and undesirable influence. So you've just got a handful of observations out of all your control units that are being dramatically upweighted. And actually, most of your control units have almost zero weight, so you're just throwing out a lot of information, essentially. And that is a problem too. Okay. So, having gone through the literature, we came up with a list of outstanding research questions that we felt hadn't been adequately explored yet. Okay. So, first of all, what should we select as the highest order of moments to match on? Obviously, the higher the value of R, 3, 4, 5, okay, then you're equating your covariate distributions to a higher order, so you're improving the balance. But then, of course, you're adding more balancing constraints in your algorithm to the point that potentially the EV algorithm won't converge and you can't get a solution. Okay? The second point, what minimum overlap between the covariate distributions is required to ensure convergence of the EV algorithm? Even in some of our simple simulation studies that we ran, we encountered convergence issues and we didn't have any way to sort of know that in advance. So being able to identify in advance what minimum overlap is required between the covariate distributions before running EV algorithm is an area of outstanding question. Most of the studies have focused on large sample data sets, so looking at small sample properties of EV estimators and also how EV performs in high dimensional data sets. When you have a large number of covariates, again, you're increasing the number of balancing constraints you need to satisfy to the point, again, where the EV algorithm may not converge. So if that's the case, then should we be performing EV on all available covariates? If not, what selection criteria should we apply? Okay. This fourth point here we found quite interesting. So all of the studies that we looked at, simulation studies, the outcome model that they used for the estimation of the treatment effect was the same as the model as they used to generate the actual data. Okay, so there was no outcome model with specification. And so that is something that we wanted to investigate further. This next point here is probably the biggest point, gap that we found. Pretty much no studies in the literature have compared ordinary least squares estimation of the treatment effect to EV, okay? So they've been really focusing on propensity score matching versus EV and have ignored the more straightforward approach of OLS versus EV, okay? So that's something that we wanted to focus on. And also, a lot of the studies tended to focus on covariance balance metrics rather than evaluation of estimation of the treatment effect. So when they're comparing PSM with EV, because obviously EV, it's a direct covariate balancing matching technique. You solve for the weights so that you equate the distribution. So you do expect EV to perform better than PSM on covariate balancing matching metrics, okay, which is what they found, okay, and they paid less attention to actual estimation of the treatment effect, which is our ultimate goal. So, having identified a list of research outstanding questions in the literature, then we wanted to narrow down and hone in on what did we really want to focus on, what did we think were the biggest gaps in the literature, okay? So our goal in running our simulation studies was to identify under what circumstances does EB provide superior inference compared to OLS and why, okay? EB, there's the extra computational challenge that you need to, or the extra computational work to solve for the EB weights, okay? When should we do that? Do that extra computational work over OLS, because OLS is much more straightforward, okay? So, like in any situation, any research problem, when you don't have much idea what's going on, you start off with simulation studies to get a better insight into what's going on. So, we set up some simulation studies to compare EB to the OLS estimator of the treatment effect, and under these specific conditions where we think OLS wouldn't do very well. So, first would be outcome model misspecification. So, for example, if the true outcome model is non-linear, but the assumed outcome model is linear, okay, then you would expect the OLS estimator to be biased. Does EB do better than OLS in that scenario? And the second point, we know that OLS can't control for unmeasured confounders. So when you have omitted variable bias, can EB outperform OLS in estimation of the treatment effect in that scenario? Okay. So that leads me on to the simulation studies that we ran. So as a starting point, we thought we would base our simulation study off the simulation study that Haymuller ran in his original paper. Okay, so I'll just take you through the setup here. So 6 observed covariates were generated. The first 3 covariates, X1, X2, X3, generated from a multivariate normal distribution, and they're correlated to different degrees. We have X4, X5, X6, all generated independently from a uniform chi-squared 1 and Bernoulli distribution, respectively. So the idea is to capture a range of covariates generated from different distributions. Okay? This is the treatment assignment model. It's a function of all the covariates X1 to X6. Okay? And the variance of the error term here, that controls the degree of overlap between the covariate distributions. So if we assign a higher variance for epsilon, that's the strong overlap scenario. So there's more overlap between the covariate distributions between treatment and control. If we assign a smaller value for the error variance, then that corresponds to a weak overlap scenario. So more separation in the covariate distributions. And then the unit was assigned to the treatment if the value of the linear expression here was greater than 0. So we ended up with approximately a 1-to-1 treatment to control ratio. And we ran our study on a large sample size. So we did try and run it on smaller sample sizes, but for a handful of simulations, even in this simulation study, when we were matching to the second order, even with a sample size of 600, sometimes the algorithm didn't converge. So we just wanted to avoid all non-convergence issues to start off with, and so we assumed a decent sample size here. Okay, in terms of the outcome design, we considered a linear outcome design that's linear with respect to all of those covariates X1 to X6, and also a non-linear outcome design, which is only a function of X1, X2, and X5. Okay. True treatment effect is 0, okay? And Haymuller in this paper focused on comparison of EB to misspecification of the propensity score model. So EB was always performed on all available covariates, but the covariates that he assumed in the propensity score model for comparison, okay, did not always correspond to the true propensity score model on the previous slide. Okay. So on that note, in our work here, we wanted to make sure there was consistency between the covariates that are selected for EB balancing and what is assumed in the OLS model. Okay. So this point here, consistency between the number of EB balancing constraints and the highest order of terms assumed in the OLS model. So if you're balancing to the second order for EB balancing, then in your OLS model, you want to be including all quadratic and interaction terms as well. Okay, so basically it means if those variables are available to balance for EB balancing on, then by the same token, they should be also assumed for your OLS model. In terms of comparing different treatment effect estimators, we've kept it very simple. So the basic raw estimator, which we know will be biased, the difference in sample means. The high-arc estimator, which is the weighted difference in means. An ordinary least squares estimate, and the treatment effect estimate will be your regression coefficient of the treatment indicator. And then an OLS model, but weighted by those, but weighted by the EB weights that we produce, okay? And we can show that theoretically 2 and 4 should give you the same result, okay? Evaluation criteria, we looked at the bias and the MSE of the treatment effect estimates across 1,000 simulations. So on the next slide, okay, here is just box plots of the treatment effect, of the bias of the treatment effect estimate under different scenarios. So if you consider just the first row, yeah, so this is just for the linear outcome design. And the first row is when we're only matching to the first order, okay? So matching the mean of X1 to the mean of X1 in the treatment group, okay? We know the raw estimator will be biased, okay? This one is for weak overlap, and that's a strong overlap scenario. So obviously, when you have a strong overlap scenario, you have less bias in your raw estimators because there's less difference in the covariance distributions. What I want to point out here is that your EB estimators and your OLS estimate, they're all equally unbiased, okay? So that's the case where the outcome model is not misspecified, okay? The true model is linear. We performed EB balancing on X1 up to X6 to the first order, and the OLS model includes all those linear terms. Okay, so here, there's no advantage of using EB over OLS when the outcome model is correctly specified. Down in the bottom row here, we're matching to the second order. So matching, say, X1 squared in the treatment group to X1 squared in the control group, and also including quadratic and interaction terms in your OLS model, okay? So the true outcome model is linear, okay? So actually matching to the second order is redundant in a sense, but we don't do any worse off, okay? You can see by the spread of the box plots that you get more variation in your treatment effect estimate when you're matching on higher order moments that you don't need to, but still everything is equally unbiased, okay? So again, this also shows us that there's no advantage of EB over OLS, okay? So the key takeaway here is when your outcome model is not misspecified, then so you're performing EB balancing on to the required number, to the highest order of moments that's included in your outcome design model, and your assumed OLS model controls for all those covariates, there's no advantage of EB over OLS. Okay, and then this is when results got interesting and were really quite painful. Okay, so this is when the outcome design is not non-linear. The Y is X1 plus X2 plus X5 all squared and the error term. Okay, so here we were thinking, if we're only matching to the first order and our OLS model only has first order terms, then maybe the EB approach will do better than the OLS approach. But it actually was the reverse situation here. Here, clearly, your EB results are biased in both the weak overlap and strong overlap scenarios, okay? And the OLS model actually did really well, okay? So this is where we started to get really puzzled in terms of what's going on. Here, we expect OLS to do worse, okay? But for some reason, okay, the OLS produced unbiased results and EB actually did worse, much worse than the OLS approach, okay? So what we think may be going on is that in the EB weighting here, we're also required to re-rate for X3, X4, and X6, okay, which are not in the true outcome model. So having to weight on those variables that are not elements of your outcome model involves significant re-weighting such that the EB weight distribution can be extreme, okay, and that leads to bias of your treatment effect estimate. That's one possible explanation for these results, okay? And so on the next slide here, I've just given you a snapshot of some of the EB weight distributions that were generated, okay? You can see that there's more extreme weight distributions in the weak overlap scenario versus the strong overlap scenario. And you can see, looking at the left-hand plots here, that the majority of your weights are close to zero, but you're getting some observations control unit observation with some really, really large weights up to like 40 or so. Okay, so very extreme weight distributions possibly occurring, which can bias your treatment effect estimate result. Okay. That doesn't necessarily, of course, explain why OLS did really well. We're still sort of puzzling over that. Okay. Here, the outcome model is non-linear, and then if you match to the second order and include interaction and quadratic terms in your OLS model, then everything does really well. Okay, but then that also demonstrates that there's no advantage of EB over OLS. Okay. And this specifically was the scenario when we tried to run it for smaller sample sizes. So even a size of 600, which is still sizable enough, we didn't expect to encounter convergence problems. Out of the 1,000 simulations, there would still be like 5 or 6 simulations where the algorithm, out of the 1,000 replications, there would still be 5 or 6 of those replications where the algorithm didn't converge. Yeah. And so, so that was like an issue that we encountered there for running the simulations. Okay, so key takeaway points from that initial set of simulation studies: no advantage of EB weighting over OLS when the OLS model is correctly specified. So if you have a linear outcome design, you match to the first order, and your OLS model includes all those linear terms, or the non-linear outcome design, you perform EB weighting to the second order, and your OLS model includes all the quadratic and interaction terms, no advantage of EB over OLS. Okay. Now, when the outcome model was misspecified, okay, so we had the non-linear outcome model, but only matched to the first order, and the OLS model was only conditioning on the first order terms, actually EB estimates can show more bias than OLS estimates. So we tried really hard to find a situation when EB would outperform OLS by playing around with the model, and we just kept going around in circles. It was actually very difficult to identify through simulation studies the exact conditions under model misspecification for when EB outperforms OLS. Okay. So we sort of got somewhere and then did it. So we thought we'd park this issue for a bit, okay, and move on to the next area that we wanted to focus on, which was another scenario where we thought EB might perform better than OLS, and that's when you have omitted variable bias. So, this other point here, the other takeaway from the simulation study that we found was that direct covariate balancing techniques, okay, they're, I guess, promoted because they're not modelling-based approaches. So the idea is you don't have to make assumptions on the model and get that correct, but they're still sensitive to assumptions that you make, specifically what covariates that you balance on and to what order. So it's not direct modelling in that sense, but you're still making an assumption on what covariates to balance on, and that will have convergence issues as well. Okay, so the other set of simulation studies that we wanted to focus on was how does EB perform in the case of unmeasured confounding? In other words, omitted variable bias. So we simplified our simulation study and focused just on 2 covariates, X1 and X2, and correlated covariates. Both generated from a normal distribution, but different means and different variances. And initially we set the correlation parameter equal to 0.5, so moderate correlation between X1 and X2. Linear outcome design and a non-linear outcome design, but here we're going to treat X2 as an unobserved covariate. So it's not going to be included in the EB weighting and nor in the OLS model for treatment effect estimation. So the OLS model is only going to condition on X1 and X1 squared, okay, and EB weighting is on X1 and X1 squared. We're just going to pretend we don't know that X2 exists, okay, and the true treatment effect again will be 0 in this simulation setting. Okay, so this is what we got. So in terms of the treatment assignment, here the treatment is positively related to X1 and X2, so both the observed and unobserved covariate. Okay, and the first row of box plots there is for the linear outcome model, and the bottom row is for the non-linear outcome model. So we expected everything to be biased, and we wanted to see, is there a situation in where EB would have less bias than OLS, okay? So in the linear outcome model, EB and OLS, you can see, are equally biased. It's biased due to ignoring X2 in the EB balancing in the OLS model, okay? The non-linear outcome model, we've now ignored X2, X2 squared, and the interaction term. And actually OLS showed less bias. So again, we came up with a scenario where OLS was doing better than EB, okay, which didn't really help what we were trying to find, okay. So then what we thought, okay, what if I reverse the association between the treatment and the emitted variable, okay? So I changed that plus 2x2 sign in the treatment assignment model to a minus 2x2 sign, okay. And then finally we found something where EB did perform a bit better than OLS, okay. So under the linear outcome model, obviously the bias before was positive, now it's negative. But equally unbiased under the linear outcome model scenario, but for the non-linear outcome model scenario, actually EB shows slightly less bias. Okay, so we're kind of a bit excited here because finally we found a scenario where we think we've broken all of this, and EB does a little bit, so EB does a little bit better. Okay, so this is something that we wanted to explore a bit more with some theoretical work. Okay. Just to vary the simulation settings a bit, we also increased the correlation parameter. So going back to the scenario where the treatment is positively related to the emitted variable, overall, increasing the correlation parameter between x1 and x2 decreases the bias, okay? But the relative performance between EB and OLS remain the same. Okay, so the idea is that even though you don't have x2 in your assumed model, because of the high correlation, a lot of the information in x2 is in the included variable x1. Okay, and same here as well. Okay, so when you reverse the treatment assignment, the direction of association between the treatment and the emitted variable increase the correlation parameter, overall decrease in bias. Okay, and the other, in terms of modifying the simulation settings, the other thing we found was that the bias increases the larger the difference in distributions between x1 and x2 for both OLS and EB, okay, but we couldn't make x2 too far away from x1 because we then also ran into convergence issues as well. Okay, so having found a scenario where EB actually did better than OLS finally, we thought we'd try and look at the emitted variable bias formula and see if we could get anywhere with some theoretical results. So this is the OVB formula in linear models. So you've got XA as a matrix of 1 plus KA variables and XB to be a matrix of KB variables, okay? And the true outcome model is a function of both the set XA and XB, okay? But the analysis model is regressed only on XA, so XB are omitted, okay? And this is the omitted variable bias formula. So the bias associated with the coefficient estimate beta 1 depends, given by this term here. So it depends on beta 2. So beta 2 tells us how important the omitted variables are in the original model. It also depends on how correlated the omitted variables are with the included variables. Okay, so there's two components that are driving the omitted variable bias: how important XB is in the original model and how correlated the omitted variables are with the included variables. So taking that omitted variable bias formula and applying it to our simulation study model, okay, so this is our misspecified model in simulation study 2, which only includes x1 and x1 squared. Okay, and I've used the asterisk to denote the coefficient estimates from that misspecified model. The true OLS model is given by this expression here, which includes the emitted variables x2, x2 squared, and the interaction term. Okay? So our focus is on trying to quantify the bias of the treatment effect estimate beta t star in the assumed model relative to the true treatment effect beta t. Okay, so here we're going to assume the following linear relationships between the omitted variables and the included variables. So here we're expressing each of the omitted variables, x2, x2 squared, x1, x2, as linear functions of the included variables. That's the treatment indicator, x1 and x1 squared. So your set of coefficients, the alphas, the gammas, and the deltas, they capture the relationship between the omitted variables and the included variables. So having assumed those linear relationships, what we're going to do now is substitute these expressions here into our true model. Okay, so we substitute those expressions for x1 and x2, x2 squared, and x1, x2 into our true model, and then you just collect all your like terms together. So you've got or your treatment indicator, terms associated with the treatment indicator, x1 and x1 squared. Okay? And then you compare this to the assumed model, and from that you can work out what the bias of the treatment effect estimate under the assumed model is. Okay, so just comparing the coefficients for the TI term, okay, you can see that the bias is going to be given by here. Okay, so the bias is beta 3 alpha 1 plus beta 4 delta 1 plus beta 5 delta 1. So beta 3, beta 4, and beta 5, they are the true effects of each emitted variable on the outcome. Okay, and then the alpha, the gamma, and the delta. Okay, they, if you recall, quantify the relationship between each of the emitted variables and the treatment indicator. Okay? So our question of interest then is, in the scenario where we observed, in the simulation study where we observed EV outperforming OLS, why is that? Okay, well, the true effect doesn't change in terms of when you use the EV weights. Okay, so but what we're changing is the relationship between each emitted variable and the treatment indicator. Okay, so our question of interest then is, well, how do EV weights affect the emitted variable bias? Specifically, are the weighted covariances between the treatment and the emitted variable reduced or increased in the presence of EV? Okay, so giving you an example here of a weighted covariance formula here. Okay, how do those EV weights change the weighted covariance between the treatment and emitted variables? And if they reduce the weighted covariance versus relative to the unweighted covariance, then we should expect bias to be decreasing, or it could go the other way. Okay, and so we think we need to do some more theoretical work here to identify for different weight scenarios how the weighted covariance changes, and therefore can we make some conclusions on whether EV will perform better than OLS or not. And I'd like to say we've completed that work, but we haven't. So I'm actually going to leave you hanging in the air. And that is our future work in terms of theoretical work that we need to get working on, basically trying to better understand some of the simulation setting results comparing EV to OLS. We still think it's important because, as you know, with the EV, there's the extra computational work to solve for those weights, and then you might not get a solution. So why don't just skip all of that and do the OLS approach, which is more straightforward. Other future work looking at small sample performance of EV, and because particularly with small samples, you can again run into the issues of non-convergence. And in expanding our simulation study setting to consider alternative outcome models, again, when OLS might not be a viable option, such as when you have discontinuity data structures, and applying our work to real data studies. And I appreciate if any of you have any ideas on some real data studies that we could test our work on. We did try some benchmark data sets in the causal inference literature, like the Lalonde data set on the job training program one, but in that one we found OLS to outperform EV. So that didn't really good enough. So then if you've got some ideas on real data studies, we could potentially investigate. That would be really useful as well. And that's it.